Okay, so today's lecture is about population growth. And here I have a picture of a bunny, some pretty sweet electron microscopy of some bacteria, and a stock photo of a crowd. And what do these three things have in common? Well, all three of these things reproduce. All of these things have some kind of population growth. So what would it look like if we took this bacteria and we gave it unlimited resources? We gave it unlimited space, we gave it unlimited oxygen, and we gave it unlimited food. And they try to do this using these things called reactors, which look something like this. But what would this bacteria's population growth curve look like? Well, let's go ahead and make a graph. So this is a population size or population growth graph. On the y-axis going up, we're going to have population size. On the x-axis going across, we're going to have time. Some people put this in generations, but going left to right is time, going up and down is the actual size of the population. So let's see what that's going to look like. It's going to look exponential. And here time isn't defined. For bacteria, this would probably mean hours or something like that. But if this were possible to give these things unlimited space and unlimited time, you would have unlimited bacteria. This exponential growth would just kind of continue forever. But what's the problem here? Well, the problem is that this is an unrealistic situation. This vessel, despite being pretty large for bacteria, is not unlimited. Eventually, they're going to run out of food. They're going to run out of space. They're going to run out of whatever kind of air they breathe, whether it's carbon dioxide or oxygen. There is no way to create a limitless population. And so you go from this exponential growth curve, which looks something like this, it just spikes on up, to something slightly more realistic, which is a logistic growth curve. And it's an S-shaped curve that looks something like this. This is, again, theoretical, and we're going to talk in just a minute about why it's only theoretical. But this shows you the carrying capacity. And the carrying capacity is a species' average population size in a particular habitat, in a particular place. So, carrying capacity can be different in different places. So, carrying capacity might be different in on the top of a mountain in the Sierra Nevada as compared to Modesto. You might be able to have more, cows be able to survive in Modesto than can survive in the Mojave Desert. Okay, so the carrying capacity is just an average number. It's a theoretical number that is the amount of organisms that can exist in a particular habitat, a particular place. So, by the way, you should know what each of these looks like. Exponential just explodes and keeps on going forever. Logistic starts off exponential and then slows down when it gets to the carrying capacity. So let's look at a more realistic population growth curve. This is theoretically a bunch of bunnies, and so you start off with like 10 or something like that. By the time you get to 5 generations, you've got a lot more. By the time you get up to around, 8 generations or whatever this is, you have several hundred. But as the bunny is noticing, something happens here. It starts to level off. It exits its exponential phase, and it's beginning to crash. That's why she is concerned, because their population is beginning to crash. It will continue to crash. It will continue to crash very, very low, well down below where it reached its peak up here in generation, 7 or whatever. But is it going to stay low? Is this population completely doomed? The answer is no. Not really. It will recover. And this is a fairly extreme example, but this is a much more realistic look at things than just like the logistic curve. So what happened here is the rabbits, let's say, found a new area. They forded a stream or something like that, and they found an area that was plentiful with food. And it was plentiful with food, and so they ate and ate and ate and ate and reproduced and reproduced and reproduced like rabbits. And eventually, at this point, they ran out of food. They went well beyond what could actually sustain their population in their particular habitat, and so they crashed. And then eventually what this is showing here, well, it isn't showing it explicitly, but what's happening here is that the natural food in the area, the natural resources, were able to recover because there were far fewer rabbits. And, you know, what kind of is happening is they're just maintaining around this area. Maybe they go a bit above it, and they go back down a little bit. Maybe they go up again, and then they come back down. So then my next question is, where is the carrying capacity for this population? Is it like up here? Is it down here where they crashed? Is it where they started? And the answer is no. This is the population's carrying capacity because, again, it's the average number of individuals that a habitat can sustain, which is, you know, right about here. After we got over this exponentiation phase and we got over this crash phase, the number of bunnies that can survive here on average is somewhere around here. Maybe that's 90 or whatever the number is. Okay, so here is the carrying capacity for this more realistic looking growth curve. Where are we as human beings? And I want to caution you because this is slightly misleading because this is going back over 12,000 years. So it kind of makes it look like these years should actually be more compressed. This should actually maybe be slightly more impressive looking. But the population increased as we developed certain things like agriculture, and then you hit the Industrial Revolution somewhere around here, and then boom, this thing explodes out into space. So humans are in a very, very exponential growth phase right now. But if you think about how these things work, we are somewhere nearing the top, I would imagine, and potentially our population is going to crash back down. We're going to run out of resources. You're seeing this in certain places around the world. We're running out of water. We're running out of potable water in certain areas. We're going to run out of food. We're going to run out of space. We're going to run out of clean air, especially the way that we are sort of polluting our environment. And so, by the way, when people say things like they're in favor of population control, this is the reason why. There are billions and billions of people on the planet. Okay, there's a lot of us. Now, do I think this necessarily? Do I think that we're going to crash? I'm not sure. I think a lot of people do. A lot of people I respect really believe this. And there are elements of it that I certainly believe that we're kind of seeing already. But here's the thing about humans is we're really good at technology. We're really good at sciencing our way out of conundrums like this one. Are we doomed to this crash phase before we level out? I'm not sure. But, if you don't want this to happen, start figuring out how you can make things better in whatever small way you can, whether that's, investing in science or becoming a scientist yourself or investing in more sustainable agriculture or just more sustainable anything. That's a great way you can help us avoid this little problem of crashing and then leveling out at wherever our carrying capacity is. So next time, the next lecture, we're going to talk about density dependence and density independence, and maybe we'll get another few topics in there.